Welcome to Frost & Sullivan's Growth Podcast. In this episode, we examine how quantum sensing is moving from laboratory research toward industrial deployment. Quantum sensors can measure magnetic fields, gravity, acceleration, timing, and radio frequency signals with levels of sensitivity that can exceed the practical limits of conventional sensing technologies. But precision alone does not create a commercial market. For quantum sensing to scale, developers must translate laboratory performance into compact, ruggedized, cost-efficient systems capable of operating reliably in real-world environments. That transition is now gaining momentum across defense, healthcare, advanced manufacturing, infrastructure, and navigation. So, what will determine which quantum sensing technologies successfully make the leap from the laboratory to industry?
Quantum precision meets industrial reality. Quantum sensing has traditionally depended on controlled environments, specialized equipment, and highly precise operating conditions. Industrial deployment creates a very different set of requirements. Systems need to withstand vibration, thermal variation, electromagnetic interference, and other real-world conditions while maintaining stability and repeatability. They also need to become smaller, easier to integrate, and economically viable. Progress in miniaturization, room temperature operation, system integration, and device robustness is beginning to close that gap. The commercialization question is therefore shifting. The industry already understands what quantum sensors can measure. The focus now is whether that performance can be delivered consistently, affordably, and at scale.
Not every quantum sensor will commercialize at the same pace. Quantum sensing is not a single technology market. Precision timing and atomic clocks currently have a clearer pathway toward field deployment. Chip-scale atomic clocks, photonic integrated circuits, and silicon photonics are making highly stable timing systems smaller and more deployable across defense, telecommunications, power grids, infrastructure, and space navigation. Quantum magnetometry is developing along another path. NV-center diamond sensors can operate at room temperature while delivering highly sensitive magnetic field measurements, creating opportunities in healthcare, semiconductor metrology, defense, and EV battery quality control. Quantum gravimetry offers drift-free gravity measurements for subsurface mapping, mining, energy, and navigation. Quantum imaging is opening opportunities across biomedical imaging, industrial non-destructive testing, and defense. Each modality has a different commercialization curve. For technology developers and investors, understanding where field readiness intersects with a compelling industry need will be critical.
Defense could provide an early commercialization bridge. One application is creating particularly strong momentum: resilient positioning, navigation, and timing. Modern navigation systems rely heavily on global navigation satellite systems, or GNSS. Jamming, spoofing, signal denial, and infrastructure disruption are increasing demand for alternatives that can operate when satellite-based navigation becomes unreliable. Quantum technologies could provide several layers of resilience. Atomic clocks offer highly stable timing. Cold atom inertial sensors can measure acceleration and rotation with lower drift. Magnetometers and gravimeters can use the Earth's magnetic and gravitational signatures as additional navigation references. The strongest opportunity may come from combining these capabilities rather than replacing GNSS altogether. Hybrid navigation architectures, integrating quantum sensors with conventional inertial measurement units, magnetic and gravity maps, classical navigation systems, and AI-based correction, could create a more resilient positioning ecosystem. Government and defense procurement can also help de-risk early commercialization while developers build the manufacturing capabilities required for wider markets.
AI could become the missing intelligence layer. Ultra-precise sensing creates another challenge: ultra-complex data. Real-world quantum measurements can be affected by vibration, thermal drift, electromagnetic noise, and other forms of interference. This is where artificial intelligence and machine learning become particularly important. AI-enabled signal processing can support real-time calibration, noise suppression, anomaly detection, sensor fusion, and pattern recognition. That changes the potential value proposition. Instead of selling standalone quantum sensing components, companies can develop integrated hardware-software platforms that convert quantum measurements into operational intelligence. Applications could range from cardiac signal interpretation and semiconductor defect mapping to submarine magnetic signature detection and methane plume quantification. The commercial opportunity increasingly sits at the intersection of quantum hardware, AI, software, and application-specific intelligence.
The race is shifting from quantum performance to field performance. The next competitive phase will be defined by a practical question: can quantum sensors demonstrate measurable advantages where they actually need to operate? Developers still face fragmented demand, specialized component bottlenecks, talent shortages, capital requirements, and limited manufacturing scale. Lasers, isotopes, photonics, vacuum systems, quantum-grade materials, packaging, and other specialized components all influence deployment readiness. This makes system engineering as important as fundamental sensing performance. Companies that combine quantum hardware with classical sensors, AI, software, and application-specific integration will be better positioned to translate precision into commercial value. The winners may therefore be determined less by who achieves the most impressive laboratory measurement and more by who can deliver a compact, ruggedized, scalable system that solves a high-value industry problem.
Thanks for joining us on Frost & Sullivan's Growth Podcast. Quantum sensing is approaching an important commercialization frontier. Miniaturization, photonic integration, AI-enabled signal processing, and stronger system engineering are bringing quantum-level precision closer to applications across defense, healthcare, manufacturing, infrastructure, and navigation. The next phase will depend on turning that technical performance into field-ready systems that demonstrate clear advantages in accuracy, resilience, and operational performance. For access to our research, competitive benchmarking, and best practice frameworks, head over to frost.com or email hello@frost.com. We'll be back soon with more to help you stay clear-headed and growth-ready.